Okay, so this is the next screencast in this chapter about matter and energy. So this next one will be dealing with the changes in matter and the energy fluctuations that will accompany both physical and chemical change. So you can see here a picture of the water cycle, which is sort of a really good example of all the physical changes that we'll be talking about. So a physical change is a change in matter that alters the substance without changing its composition. So you know that when water freezes, it goes from the liquid state to the solid state, but you still have water molecules, H2O molecules in the substance. You haven't chemically changed the substance at all. So all of the phase changes or changes between states are physical changes. So boiling, freezing, melting, condensing, all of those describe physical changes in matter. And there's another example of physical change that a lot of students tend to confuse. So here's our example, cobalt chloride again, which we know is a compound made up of cobalt and chlorine atoms, and it's a solid pink compound at room temperature. And then we have water, which is another compound, and we'll assume this beaker is completely pure water, so H2O, and it's a clear, colorless liquid at room temperature. But what if we mix these two together? What do we get? All right, so this is the result, and you can imagine if you actually saw this happening that there wouldn't be a big exciting change happening. The solid would slowly disintegrate or dissolve into the liquid water, and you would end up with this mixture of cobalt 2 chloride dissolved in water. But dissolving is only a physical change. I could still get back the solid cobalt 2 chloride and the separate water using a process that uses physical changes. So chemically, I haven't changed either of these substances at all by combining them into this mixture. And that's one of the key differences between chemical change and physical change is you don't change the identity of the substances. So the process that we can use to get those two compounds separate again is called distillation. And it's a separation technique that's based on the differences in boiling points of substances. So if cobalt 2 chloride is a solid at room temperature, you know that it must have a much lower melting point than water, which is already a liquid at room temperature, and it has already melted. In fact, it melts at about 0 degrees Celsius. Sorry, the cobalt 2 chloride has a much higher melting point, much, much higher than water. So it's sitting there below its melting point in a solid state at room temperature. So the reason we have to use distillation is because the particles of cobalt 2 chloride are too small to separate with a filter. So the process depends on heat, adding heat to the system, and then we bring one of the substances to their boiling point. In this case, water. It'll boil much faster than the cobalt 2 chloride or the salt in the water. And it'll go up into this tube, and then it'll get collected in a distillation tube and fall into another container where it can be collected as pure water again. And eventually, once we heated it long enough, what would be left behind here is all of the cobalt 2 chloride or the pink solid. So that's one method of separating mixtures that relies on physical changes. Okay, there's another method called filtration, which is how you would separate a heterogeneous mixture when the particles are big enough to get trapped in a funnel. So if you had a mixture of sand and water, for example, or say you crushed up chalk and put it into a container of water, and then you wanted to get the water separate from the chalk again, you could use filter paper and a filter and gravity and just pour the mixture through the filter paper, and the water would come out the bottom and the solid would get stuck in the filter. And then one last method of separating mixtures based on physical properties is a process called chromatography, which separates compounds based on their tendency to be attracted to a substance. So in this case, the red has the strongest attraction for the paper or the chromatography film that this is taking place on, and the yellow has the lowest attraction. And the yellow would also have the highest attraction for the solvent, which is pulling all of these compounds through the paper. And it would have, and red would have the lowest attraction for the solvent. So this method separates substances based on their attraction for different types of compounds. So the physical changes that we talked about earlier, the changes in state, are of course very, very familiar to you, right? A substance changes from a solid to liquid when it melts, and it melts at its melting point. It also changes backwards from a liquid to a solid. when it freezes. These two phase changes occur at the same temperature. Okay, we often say it's melting point, but you could also call it the freezing point. They are the same temperature. So for example, water freezes and melts at 0 degrees Celsius. That's where those phase changes occur. So, and then a liquid can change to a gas by evaporating, or sometimes it's called vaporizing. Or with water, we like to call it boiling, right? When we see the little gas bubbles. And the gas can change back to a liquid when it condenses. Again, both of these phase changes occur at the same temperature for any given substance. It's called its boiling point, and that would be 100 degrees Celsius for water. There's a fifth phase change that you don't see very often. It's called sublimation, when the solid changes directly to the gas without going through the liquid phase. And that only happens with a few particles at a time. It doesn't happen at a particular given temperature. It's under certain specific conditions. But you'll notice also that as the energy is increasing, we're moving up this diagram from the solid to the gas. So for the same substance, the lowest energy state would be the solid and the highest energy state would be the gas for those particles. So if we think about those phase changes, if a substance changes from a solid to a liquid, if we're talking about ice or water, we'd be talking about ice to liquid water. That's a process where the ending substance has more energy than the beginning substance. So that's an endothermic process, because in order for this change to happen, this system, the ice cube, had to take in energy from the surroundings. That's how that phase change is enabled to happen. So any process that requires energy is known as an endothermic process. All right, so the opposite of that would be an exothermic process, and that's any change where the starting substance is at a higher energy level than the ending substance. So in this case, we start with water vapor, and it condenses into liquid water, right? Well, in the process, the liquid has a lot less energy contained in its particles than it started with as water vapor. So that process will actually send energy out to the surroundings in the form of heat, usually, sometimes in other forms. But energy leaves the system, the water in this case, and goes out into the surroundings. And that's an exothermic process. So here's another slide that just shows those same phase changes. And when you melt or evaporate a substance, you have to add energy to the substance. And when the substance goes through condensation or freezing, that's energy will leave the substance and go into the surroundings. So the bottom of this screen is actually the exothermic processes, and the top of this image are the endothermic processes. So energy, for now, you really only need to know a few things about energy. It is defined as the ability to do work, and work just means moving a mass over a certain distance. Energy is conserved, just like matter, which means it's neither created or destroyed during physical and chemical change. It does flow from one type of matter to another. It flows through systems, and it's measured in joules, which the symbol for that is a capital J. So there's a lot of different forms of energy. Some of these you're familiar with and some maybe not, but there's two big categories. There's potential energy or stored energy, and there's kinetic energy or energy of motion. And I know you're familiar with these two forms from your 9th grade science class. So when energy is in action or is actually moving, that's pretty much kinetic energy. So wind energy, water energy, if it's moving through a dam or water moving in a river. Electromagnetic energy, light, electric energy through a current, through a circuit. And then there's thermal energy, which is the energy possessed in the motion of the particles, and it transfers from warmer objects to cooler objects, right? Those are all forms of energy of action. And then we have potential energy, so anything that's stored. So potential electric energy would be a battery, or gravitational potential energy would be that water that's behind the dam that hasn't been released yet, and it has all that energy stored up in the mass and the height of the water. You have chemical energy, which is a form of stored energy in the form of food or fuels. Okay, so those are all forms of stored energy. Temperature is really the way that we look at changes in energy, or that we can measure changes in energy in the chemistry lab. So it's a measure of the average kinetic energy of the particles of a sample. And when energy flows into a system from the surroundings, that means the temperature of the surroundings are going to drop, because we're taking that thermal energy out of the particles. We're dropping the kinetic energy of the particles, because that energy is going to go into something else, into the system, melting ice or something like that. That's endothermic. When energy flows out of a system, the temperature of the surroundings will increase. That's an exothermic process. So when you burn a match, for example, you see the energy leaving the match, the system of the match head, and going out into the surroundings. And you can see it as light, and you can feel it as warmth or heat. Okay, so those are different ways of thinking about those two, the same two terms, endothermic and exothermic. So the two temperature scales that we're going to use in chemistry are the Celsius scale, which most of you are already familiar with. You should know that water freezes and melts at 0 degrees Celsius, and it boils at 100 degrees Celsius. Now, the Kelvin scale is called the absolute temperature scale, and it's the one that usually is used in most science laboratories. And it's defined as at absolute 0 is 0 Kelvin. So there are no negative Kelvin temperatures, right? And the Kelvin temperature scale is just simply 273 degrees higher than the same temperature in Celsius. In other words, this is how you get Kelvin. You take the Celsius temperature and you add 273. So the unit 1 Kelvin represents the same amount of temperature change as the unit 1 degree Celsius. If the temperature goes up by 1 degree Celsius, it's also going up by 1 Kelvin. So in that respect, they're similar. It's just that their 0 point is different, is defined at a different point. So the other type of change that we're going to see in matter are chemical changes. And chemical changes are those changes that involve the formation of new substances, right? And what's the evidence that you have a new substance forming? Well, there's a lot of different things you might see, but things like decomposing or rusting or exploding or burning, oxidizing, these are all words that describe chemical change. Now, what are you going to see as evidence of chemical change? Well, you'll often see a change in color. Not always, but often. You'll often see changes in energy that accompany chemical change, either exothermic, meaning energy will be given off like a flame, or endothermic, meaning the reaction will actually feel cold or will take in energy. You might notice a change in smell if a new product is formed, especially if the product is a gas. You might see a gas forming in the form of bubbles, or you might see a precipitate form, so a solid actually forms out of solution. But usually there's going to be some very dramatic evidence that a chemical change is taking place. So that's all for today. Make sure you fill in the vocabulary words for the summary sheet and bring that to class with you tomorrow.